All right. So, does anyone else have any more questions? Okay. Thank you, sir. All right. So, if there are no more questions, what we will do is we will start our lecture on 1D steady convection diffusion equation. So, this is as usual. It's an interactive session. You can ask me doubts anytime. You can stop me in between. Not a problem. So, what we will do today is yeah, so what we will do today is we have this convection diffusion equation. It's a 1D steady convection diffusion equation because there is no d by dt term. Uh, so this equation is actually you can solve it analytically. You don't need numerical methods or CFD to solve it. But what we will do is we will try to solve it using CFD or numerical methods, finite difference method, and by doing this we can understand a few things related to steady state problems, like what should be my minimum or maximum delta x in my domain to have a bounded or stable physical results. So what should be my minimum delta x? So what we saw in the last class was regarding stability of unsteady flows, unsteady equations. But what about steady state equations? So does that mean steady state is always stable? Um, so you will come to know that's not the case. Few it depends on the it purely depends on the discretization scheme what you use for each term. So we will quickly derive the analytical solution also, which would be helpful to understand few physical concepts. Um, so if we look at this equation,
Hello,
it has
sir.
yes, yes, Suzanne.
Sorry to interrupt. Sir,
No problem.
can you explain that integral equation? Means like if for finite volume, but means in that lectures, sir have told about finite volume equations.
Right,
Means like there is one integral equation. So
right,
I was
right.
not able to understand that equation. So could
So
you please explain that?
right, right. So
Hmm.
so what is integral equation is it's nothing but it's a differential equation but written in integral form. So let's say you have a continuity equation. What is your continuity equation? Dou u by dou x, dou v by dou y plus dou w by dou z equal to 0, right? Or you can simply write del dot v equal to 0, where v is u I, v j, and w k. Okay. So now this is the differential equation. You can use finite difference to solve this, right? You can use finite difference, but it may not. The main issue with finite difference is it may not ensure the uh, conservation principles, like your mass might get added or subtracted somewhere here and there. So to ensure the conservativeness of the method, we go for finite volume. So basically in finite volume what we will do is we will consider a volume, a control volume, and we will apply this equation for this volume. So how will you do that is you have to integrate this equation for a small volume. Okay, so if you integrate this equation for a small volume, so this is control volume, you just need to integrate it the differential equation for a whole control volume, then you will get what is called the integral equation. So if you do this integration over control volume, what happens is, can you guess what happens after this? You are just integrating the differential equation over a control volume. any arbitrary control volume. So can you guys come up with any mathematical theorem to simplify this, or is something striking in your mind? See, it's a divergence of velocity or divergence of a vector. You guys know Gauss divergence theorem? What we will do in Gauss divergence theorem is, right, uh, Gauss divergence theorem, we will convert this volume integral to an surface area integral. So if this is the control volume, let's say in 2D, okay. So now we have uh, this is control volume, this is control surface, right? So now what we will do is we will convert this control volume to a control surface integral. It will be v dot n ds. Okay, this is a Gauss divergence theorem. You can have a look at it. So what happens is your differential equation, differential means it is when delta x tends to 0, or it is specified for a point in your domain, right? But if integral equation is it's for a whole control volume. So what you are doing essentially is you are integrating the continuity equation for a control volume. That is usually a finite volume method. So after integrating that equation to a control volume, you are applying Gauss divergence theorem to get v dot n into ds. Um, so so this is what finally becomes this only you will this part you will solve for. So let me write it separately. So this del dot v equal to 0 becomes control surface integral v dot n ds equal to 0, right? So you need to find what is the flux crossing each surface. Just need to find flux crossing each surface of that control volume and you will satisfy the conservation principle. So that is how it is done. The divergence of V is converted into a integral form of equation. So these both are equivalent. Okay. Does that make sense? Is it?
Yes, sir. Understood.
So Ganesh,
Uh-huh.
Ganesh, I'm Divakar here.
Yeah.
So Ganesh, actually, I have a basic doubt actually, which is generally we are dividing the see when we are talking about finite element methods and finite volume methods, we are saying that we will split in the finite volume methods. Actually, body will be split into the specified volumes actually into the volumes. Whereas in the case of finite element methods, we will split into the elements, something like that. Professor has actually explained.
Correct.
Even before lectures, also I have heard
Right.
something like that only. So, what exactly the physical meaning of splitting into volumes and elements? Because if you take any 3D body, splitting is splitting itself. Either you take as finite volume or finite elements. It got some volume, so like it's kind of you understand, right? Both actually same kind of thing. No, when you are split actually into when you split the body into some number of parts actually, either you take finite elements or finite volume, both will be the same volume, no, like same entity. So
Right.
what
Right.
actually exact difference between finite element methods, finite volume methods, in case of meshing actually, when you are splitting them like something into volumes or elements physically? That's what actually my doubt, Ganesh.
So I'm not fairly familiar with finite element method, but I can give you few insights. Basically there are three types of method: finite difference, finite volume, and finite element method. So in finite difference method, what you are doing is you are solving for nodes, like in each and every node what is my data. So if you go to finite volume method, you are dividing this domain. In finite difference, you are dividing this domain into number of points. In finite volume, you are dividing this domain into number of control volumes actually. Okay, so the main difference between these two is if let's say there is a differential equation, everything at the end is differential equation. Like if there is a differential equation, you can solve it either with finite difference or finite volume, there is no problem, or finite element for that case. So but why we need to go to these two different methods? Because anyway we are dividing the domain into number of small elements. So the major difference is if you are solving a fluid flow problem, um, you know it's the fluid is going to enter and the fluid is going to leave, uh, right? So let's say if this is a control volume, the fluid will enter in this surface and a fluid will leave this surface. I'm not talking about one control volume. I'm just generally talking about a physical domain. Any physical domain, fluid will enter from one surface into that volume and it will leave some at some other surface, right? So that is how the physical fluid flow problem is defined. But you see, if you use a finite difference method, uh, it the definition of finite difference method is you are dividing the domain into small points, right? So from where you will make the fluid enter, or from where you will make the fluid leave. So from fluid flow perspective, finite difference doesn't make more physical sense. Like that's why people went to finite volume. Like if you want to divide the domain, a 2D domain, let's say, it will be like just some number of nodes here and there, right? So um, it, it will be like this. But in fluid flow problem, we know that it's actually it's like it enters, it has some flux, fluid has some flux, it enters our surface, it leaves the surface, there is an expansion or contraction happens within the volume. So all these concepts doesn't make sense if you apply it for a node. That's the basic thinking, that's why they went to finite volume method. And one more thing is, let's say if you have a domain and some fluid is entering, let's say 5 kg is entering, and let's say this is the opening and some kg, let's say 5 kg is leaving. So if you apply a finite volume method, right, if you divide the domain into small control volumes and if you try to analyze it, you will ensure that this and this would be same. Or let's say if something stays, 3 kg will come out, like 2 kg stays inside. So those things would be ensured, the mass, momentum and energy conservations would be ensured if you use a finite volumes methods. So if you use a finite difference method, you may end up like goes in with 5 and it might come out with 5.1 kg, even though when there is no source term inside the domain, right? So those things can happen in finite difference method. Those conservation cannot happen, you cannot ensure conservation in a finite difference method, but you can ensure it in finite volume method. Coming to finite element method, it's actually purely used in like strength of materials, like finding the stresses there, because they the, they consider everything as a small elements connected, like small links connected with each other. So there in a solid perspective, finite element makes more sense. uh, Finite volume doesn't make more sense because volume is not going to, like solid is not going to flow, right? So that's why people go for finite element method when they do a stress analysis also. But nowadays CFD is also done in finite element method. I am not entirely sure about finite element method, but the basic difference is between finite difference and finite volume is this. So do you have more a specific question? Did I answer your question?
Yes, Ganesh, I was actually asking the overview only. I hope you have cleared some of the information. And in the in the finite, you see, actually in the finite difference, actually the information will be stored at the nodes you only mentioned. I agree, you're right actually, somewhere I read. In the finite volume methods, where we will store the data? In the center of the volume of single volume of how it is? You understand my question?
Right, right,
Ganesh?
right, right, right. So let's say you have in a finite volume method, there are two types of approach, which eventually you will learn. One is a simple mesh, I guess. Another one is, yeah, collocated and staggered. So there are two ways to store the values. Collocated, right? Yeah, and staggered. So you will soon learn about this in coming lectures also. So what it means is, like in collocated mesh, there will be one mesh, but you will store the values in the center of the cells, right? But this value is representative of the whole control volume. Okay, this is a integral value of that control volume. It's not just the nodal value, right? But it is stored at the cell center. This happens in the collocated mesh. In staggered mesh, what they will do is, because to ensure conservativeness, similarly when you solve a Navier-Stokes equation, you need fluxes at this control surfaces. So at that time, what they will do, the mesh for velocity, u velocity, v velocity, and pressure would be different. It will be staggered a little bit. So that you will come to know. But essentially, in a finite volume method, we store it in the cell center, but it's an integral value of the control volume. So let's say this is the uh, value is actually integral of phi of x x y z times d volume. Okay, so this is the value you will find using finite volume method, but it is actually a integral value of a control volume. So that is the basic you know sense inside it. Is that clear, Divagar?
Yes, Praveen. Yes, Ganesh. Thank you.
Okay, so these collocated and staggered mesh you will soon learn in an upcoming classes while solving doing this solution to Navier-Stokes equation. So whatever the equation we studied till now is just simple normal equations, but when you come to Navier-Stokes equation, you have to deal it a little bit cautiously, because you need to solve four equations simultaneously, like for three velocity and one pressure. So does anybody have any more questions?
Any idea about turbulence models, Ganesh? I got some doubt in it.
So actually
You
I
asked if
haven't.
you're allowed.
I haven't worked in turbulence models, so uh, I may not be able to comment on that. So I haven't worked in turbulence.
Okay, Ganesh. Thanks for it.
Anyone else? Okay, so if there are no more questions, let me continue with what I plan to do. So here we have convection diffusion equation. I remember one of them asking questions about how about stability in a steady state equations, right? So usually if there is a steady flow, let's say steady state flow, usually in commercial softwares, or what if you, even if you write your own programs, what you will do is you will include unsteady part, you will solve it for a very long time until the properties or variables doesn't vary that much. So that's how you will solve a even a steady state problem. It is very difficult to solve a steady state equation. It is rather easy to solve an unsteady equation. So it's because of the complexity of a PDE it arises. So that is apart. But if you have a steady state equation, um, you can apply the von Neumann stability analysis here, right? So how are we ensuring boundedness of the solution, or physical uh, you know like the solution we get, is it physical or not? How do we ensure that, if it is a steady state equation, if you are solving a steady state equation? So this is a steady state convection diffusion equation, um, right? So like it has a convection term rho u phi, and it has a diffusion term. So if I let's say, so this equation has actually have a uh, analytical solution if you consider rho u and rho u to be a constant. So if you consider rho and u to be constant, you are going to have a analytical solution for this equation. So let's first derive that analytical solution. From there you will get to know the convection and diffusion dominance in a flow problem. So what we will do is we will take rho and u outside, because it's a state, like it is a constant. So it will have dou phi by dou x equal to gamma is also constant. It's a diffusion coefficient, square phi by dx square, right? So if I rearrange it, what will I get? D square phi by dx square minus rho u by gamma d phi by dx equal to 0. Okay. So what we will do is we will assume a variable called a. It's not variable, actually constant a, which will be rho u by gamma. Okay. So if you see this is going to be we know what is Peclet number, right? You guys must have gone through the lectures. Peclet number is nothing but convection flux by diffusion flux, right? Or convection by diffusion, however you say. So we know that it is going to be rho u by gamma times L, length. So if we look at these two, this would be rho u L by gamma, right? So Peclet number is rho u L by gamma, A is rho u by gamma. So what we can do is we can write it like this. We can write A to be Peclet number by L, right? So let's try to solve this differential equation. If we solve this differential equation, what happens? D square phi by dx square minus A times d phi by dx. So we all know how to solve this equation, right? It's a second order ordinary differential equation. So how do we solve it? And write it like this, right? D square minus AD times phi is equal to 0, right? D is a differential operator by dx, right? So what we can say is we can assume that phi might take a um, solution of form e power mx, right? Substituting it in the equation, will get m square e power mx minus a times a m e power mx, right, equal to 0. So if you cancel out this thing, m square minus a m equal to 0, this would be your auxiliary equation, right? Am I right? M into m minus a is equal to 0. Then m would be 0 and a. So what would be your solution? Phi would be c1 plus c2 e power ax, right? It's fairly simple, right? So if we continue, if you how do we get c1 and c2? How do we get the constants?
By using boundary conditions, we have to substitute and then get it.
Right. So our boundary condition is phi at x equal to 0 is phi naught. Actually, it's 0. So if we go back here, we have it here. Phi at x equal to 0 is 0, and phi at x equal to L is 1. Right. So if we do that, phi is equal to x equal to L, phi L is equal to 1. Right. So if you substitute it, um, so in the interest of time, I'm just writing the solution. You all might know this. You all are expert in this anyway. So it's going to be phi of x would be phi naught, which is 0 actually, plus phi L minus phi naught divided by power Pe minus 1, because L is equal to 1. So Pe by L becomes 1, power Px minus 1. Okay. So if we simplify this also, what would happen? E power Px 1 divided by e power P minus 1, isn't it? This would go to 0. Phi of L is 1. 1 minus 0 is 1. And so this part remains. Right? So you can check this. So this is the
Hello.
so this is the analytical solution here. Yeah, Nidharan.
Uh, Actually, I have a doubt regarding phi. How we assume, how we take the solution of phi will be e power mx.
So actually the you can it's like assuming that phi is equal to e power mx, right? So usually we used to solve this equation, right? How we will solve? We will assume phi equal to e power mx, and we will substitute here, then only we will get auxiliary equation, right? uh, do you remember solving this kind of equation, a second order differential equation?
Yeah, we shall actually we just equate d square minus ad equal to 0 like that. We will get the terms for d like that. Actually,
So
we will replace d in terms of m only.
right. So actually it is a shortcut, people just skip it. So actually how it comes is, you assume that phi is equal to e power mx. It's an assumption, like phi can take a form of e power mx. So any solution can be expressed in exponential terms. Okay, so this m can be real or complex, it doesn't matter, but solution can be expressed in exponential term. Okay, so when you substitute this only, you will end up getting this equation. So people
Yeah.
usually skip this, but this is how you will get the auxiliary equation. It's just
Okay.
trying to you can go through your maths textbooks, like um,
Yeah. Okay. Okay. I
so
got understood.
this is how it starts actually.
Okay, so generally we assume we take phi in terms of exponential manner.
Right. So then only you will end up with auxiliary equation. What people usually does is they will just put d is equal to m. But this is how. But anyway, if you just put d is equal to m, you will end up with the same equation.
Yeah, yeah.
But the essence is it comes from there.
But do you know why we are taking that solution in terms of exponential manner?
So exponential manner, actually solution. Um, how do I put it? So if let's say if it is a real, if it's a complex, it's going to have cos and sine, and if it is a real, it's going to have exponential. I mean, any solution can be expressed in terms of exponential terms. That's the basic mathematical principle comes into picture. Uh,
Okay, okay,
so
okay,
that's how this auxiliary equation comes.
okay, 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 brother, fine.
Okay. So
Thank you.
yeah. So let's say if this is the phi of x, okay. So this is this is exponential in nature, right? This is going to be constant. This is e power pe, times x minus 1. So let's say if you want to plot it, okay, so what if the Peclet number, let's consider three thing, Peclet number equal to 1, how would be our solution? Can you guys guess? So we know that boundary is here, it is 0, right? So here it is 0, so curve starts from here, and at x equal to 1 we know that phi is equal to 1, so curve ends here, right? So internal, it can be like this, it can be like this, it can be like this, or it can be like this also. So how do you expect it to happen? What happens if Peclet number is 1? So let me just give you the solution. Actually, when Peclet number is equal to 1, what happens is this would be uh, uh, the solution. So you can go ahead and you can after this class you can check whether it is correct or not. But when the Peclet number is equal to 1, it's going to be the uh, actually sorry, it can't be, right? When Peclet number is equal to 0, what happens is uh, this this whole thing becomes
0, sir.
right. Do some mistake here. So Peclet number equal to 1. So 0 would be 1. 1 minus 1 is 0. Right. Right. So hmm. So still depend on the absolute 1 by e power p minus 1. Peclet number is 0. This part goes to 0. Right. So what happens to this equation when p is equal to 0? Phi of x is equal to e power 0 minus 1 divided by e power 0 minus 1, right?
It will be kind of indeterminate form.
Right. So this equation may not be valid for Peclet number equal to 1. Okay. So but if you try to get it from some other way, your Peclet number equal to 0 would be like this. Okay. You cannot get the solution when Peclet number is equal to 0. But let's not worry about Peclet number equal to 0, because that's not going to happen. If Peclet number is 0, means convection divided by diffusion is equal to 0. So let's not worry about that. Anyway, we have both convection and diffusion. Let's say our Peclet number is greater than 0. What this means? Convection is greater than diffusion, right? If Peclet number is greater than 0, convection is greater than diffusion. So how will our curve look? So if you try to plot it in MATLAB, or if you try to plot it yourself in some other softwares also, your Peclet number, if it is greater than 0, you are going to get curves like this, right? When Peclet number is greater than 0. Similarly, when Peclet number is less than 0, you might have guessed by now, going to be like this. Less than 0. Now you see, this is our solution looks like. So if there is a velocity is 1, which means positive, there's going to be convection current, u is equal to 1, and diffusion is going to happen in all sides. That's what diffusion means, right? It doesn't take any direction. It happen in all directions. So if you see the convection is happening this side, and if there is a heavy convection, what we are going to see is you are going to see a profile like this. Right? If it is less than 0 means it's in the opposite direction. So you are going to see a profile like this. So let's say if you try to model it, okay, using this is of less interest right now, but so why we do this is our aim is to model it using finite difference method and to compare the solution with the numerical, compare the solution with the analytical. So let's try to model it using this finite difference method, whatever we learned. So if you let's say you have you know that second order derivative can be used like this. What is this called? Central differencing, right? So this is for second order, and this is for first order derivative, right? You can approximate it like this. So what is this scheme?
Forward difference.
Backward.
Right. Actually, it's backward because you are taking from I minus 1 to I, right? It would be forward if you take from I to I plus 1. Okay, this is upwind or backward. Okay, and this is going to be central.
Center difference.
Right. So now there are two ways to model it. There are few more schemes also you can try it, but one thing is you can use this. You can use this, and for first order derivative you can use this, right? So let's say you are trying to model this. So the equation will have first a second order derivative, which would be phi of I plus 1 minus 2 phi I phi of I minus 1 divided by delta x square minus a times d phi by dx, right? What is our equation? Uh, so this is our equation, right? Minus a times d phi by dx equal to 0. So how do we do this? Phi of I minus phi of I minus 1 divided by delta x equal to 0, right? Let's say you are let's couple these two terms, like we will take a common let's write it in terms of nodal values. It will be I plus 1 plus a of I into phi I plus a of I minus 1 into phi I minus 1 is equal to 0. So this is actually, what is this scheme? This is UDS, upwind differencing scheme. This is central, right? Similarly you can do for CDS also. Only thing it's going to change is coefficients, right? So let's write the coefficient for this. What would be AI plus 1? AI plus 1 as 1 by delta x square, right? We doesn't have I plus 1 here, so it should 1 by delta x square. What would be AI? AI will have 2 by delta x square minus a by delta x, right? Similarly we have AI minus 1, which would be 1 by delta x square and then plus a by delta x, right? So a is going to be constant, so coefficients will be constant for all the three sets of equation. So let's say if you want to solve this, how we are going to solve this? So it was a differential equation. This is your this whole thing is your discretized equation. Your discretized equation, and the coefficients take off this form. This is UDS plus CDS for second order. Similarly, you can get coefficients for the CDS plus CDS of second order. Okay, so how will you write? Let's say you have this domain. Say this big domain you have. it starts from I equal to 1 to I equal to n. So what you will do is you will try to write this equation for each and every node. Okay, for let's start from I equal to 2. Okay, I equal to 1 and n are boundary nodes. Let's treat it separately. Let's start from I equal to 2. What will happen? It will be a1 phi 1 plus a2 phi 2 plus a3 phi 3 is equal to 0. But we know that phi 1 is known. A1 is actually 1 by delta x square. Let's not write a1 because it might get confused. What we will do is we will write it like ai minus 1, ai minus 1 phi 1 plus ai phi 2 plus ai plus 1 phi 3 is equal to 0, right? Similarly, for I equal to 3, what you will do? ai minus 1 phi 2 plus ai times phi 3 plus ai plus 1 phi 4 is equal to 0. Similarly, you will write for I equal to n minus 1. Let's write for I equal to n minus 1. ai phi of n minus 2 plus ai phi n minus 1 plus ai plus 1 phi n plus 1 is equal to 0. Now what happened? You have 2 to n minus 1 equations, a set of equations, linear algebraic equations. So how will you write this? So we can write this in a simple matrix form. So is this clear till now? How did I write for each and every node? It actually comes from this equation, the discretized equation. Okay, I substituted I equal to 2 to n minus 1 to get different set of different equations. Okay, so let's say if I put it together in a matrix form. Before that we will do one more simplification. You see, at I equal to 2, we know the value of phi 1, and ai minus 1 is already known, right? So what you can do is you can put it on the other side. Similarly, here phi at n plus 1, it's not actually n plus 1, it's n, right? So similarly, phi at n we already know, so you can put it on the other side. Okay, so what if we try to write a matrix for this? The first equation will start from phi 2. So there is some matrix here, some A matrix, and we are going to write in terms of phi 2, phi 3, phi 4 to phi at n minus 1 is equal to some B matrix, right? So how will A matrix look? So we just need to you know get the coefficient of this multiplication. So the first equation actually has phi 2 and phi 3. Phi 1 goes on the other side. So what happens? This becomes ai and ai plus 1, and remaining else it doesn't depend on 4 phi 3 4 phi 2 n, right? So those things would be 0, how much ever you want. So how much ever node is there. Similarly, for the third, this equation will take this form, right? If we keep on writing like this, so what will happen? There will be this three, right? So you will end up getting this kind of matrix, a tridiagonal matrix. Okay, since it's a 1D, you end up getting tridiagonal matrix. If it's a 2D, you are going to have other two sides also. You will end up getting 4-dimensional matrix, like pentadiagonal matrix. You will have another one more diagonals. So what happens at B? So we took this term on the other side. and similarly this term on the other side. So we need to put that there. So how do we do this is minus a I minus 1 phi of 1, which is actually a boundary node, which is actually phi naught, right? Similarly here also phi a I plus 1 and phi of n, which is actually phi l, right? So now you have a phi b, that is the equation we have, a phi equal to b. So we just need to get phi. What we can do is we can inverse it, that's all, a inverse of b. Now you will get phi at every nodes, right? So if you perform this inverse operation, so that this is how you will find a this is how you will use numerical, whatever discretization scheme you use, we'll just cast it into a matrix. We'll write a equation for each and every node, we'll cast it in the matrix, and we will just invert the matrix to get the solution. So this is how we will get. If you give 5 minutes, um, maybe I will finish a little bit of it. Can I take a 5 minute?
Yeah, sure.
Okay, okay. Sure. So, so what I was trying to say is, so this is phi is equal to a inverse b. So this is how you will get phi. So you can do the same thing. You just need to find the coefficients. Similarly, you can do for this is actually done. This is actually common for both CDS or UDS, whatever scheme you use. Only thing is coefficients might change. Coefficients will change. So here the coefficients are 1 by delta x square minus 2 by delta x square by a, these three coefficients. If you are using central differencing, what you are going to get is you are going to get different coefficients. So what you can do is you can try getting a coefficient, and you put it in a matrix and you solve it. Okay, so you can write your own MATLAB program to solve this set of equation. So you solve this equation and you plot the solution. Okay, so if you do that, I will show you. So I've already done that. So I won't show you the program, because I encourage you to program it, like for the, so if you just change the scheme, you are going to get a different solution. And similarly, if you change the nodes, you are going to get bigger matrix and you are going to get more accurate solution. So I want you to program it, so I am not going to show you the program thing, but what I will do is I will show you the results. So give me 2 minutes. So is my screen visible?
Yeah, okay.
So were you able to see a MATLAB app?
Yeah, we can see.
Uh, were you able to see or no? I'm not getting it.
Yeah, sir, we can see it.
Okay, okay. So what we are going to do now is we are going to play with Peclet number. Let's say we have Peclet number of, let's say, 20. Okay. So what Peclet number of 20 means? So
Term is more.
right, right. So
Dominant.
convection is more. How big? So it's going to be 20 times the diffusion, right?
Yeah.
Right. So let's say you have 10 nodes, okay, from 0 to 1, okay. In this graph, you have 10 nodes, okay, and you want to plot a 5, okay. Now let's say I'm using upwind differencing scheme. So whatever we develop the coefficients here, I used it to for 10 nodes to get the solution. Let's say if I'm calculating it, can you see the solution here? So this red line is actually exact solution at each and every node using the exponential solution we got, right? We derived it. So using that derivation, we got this curve, the exact solution curve. Similarly, if you do this upwind differencing, if you solve this matrix using this upwind differencing scheme, you will end up getting this blue line. Okay, so what we will do is, we have 10 nodes. 10 nodes means how many elements we have, like elements in the sense how many delta x we have. We will have 9 delta x. So 10 nodes include a boundary node also. So in between we have 9 delta x. So let's say I'm changing this to central differencing. Okay, is this clear, like what I'm trying to do?
Yeah, we can able to understand.
Yeah, okay. So let's say I'm changing to central differencing scheme. Okay, so what will happen here is, can you see this? So here again the red is exact solution and blue is you know, the numerical solution. But you see the value here is minus 0.05. So phi is bounded from 0 to 1, but you see when you do it using central differencing scheme, your value is reducing to minus 0.05. So what this means is, um, like, what is the boundedness criteria? Why for central differencing there is a it is giving unphysical solution, so you can't get a phi negative, right? It is from 0 to 1 only, right? It is some scalar, it's a kind of scalar transport. The scalar can't be negative, mass can't be negative, let's say. So if you change it to upwind, you see you are getting a physical solution which may not be accurate because there are some errors. But if you change it to central differencing, you see you are getting a unphysical solution. So the 10 nodes what we use is not enough to capture the full physics for a central differencing scheme. Even though it is second order accurate, it was not able to capture. The main reason is, uh, uh, if it is a second order accurate, if it's the even order accurate, right? So then the next term would be delta x square, order of delta x square. The truncation term would be order of delta x square. If that is the case, you might have heard that there would be a dispersion error, right? Dispersion error usually leads to unphysical solution. So this is what you are actually seeing it here. Like, so you might ask me that what is the delta x, minimum delta x I should use to get the uh, proper solution, right? So let's say let's change this to, let's increase the Peclet number. What will happen if you increase the Peclet number? What do you guys think?
The graph will shift towards our right hand side, sir. It approaches one, I think.
Right, so it is true. So you see the exact solution. I'm plotting it for each and every node, so you may not see the curve, but at point, let's say at point 888, this is the value, exact value. Okay, so but you see the central differencing having these oscillations. This is called dispersion error, which comes with the derivative. So now what you can do is, you can see that Peclet number 50 means the convection fluxes are more than the diffusion flux, but you are using CDS scheme which doesn't take direction of flow into account. So that is a major reason for this to happen. So if you change it to upwind scheme, you are going to get normal results, like you are going to get physical results. Like, it may not be accurate, but you are going to get physical results. But if you change it to central differencing, you are going to get this unphysical oscillation. So when can we stop this is, your local Peclet number should be less than 2. That's how you will stop this from happening. Let's say you have a Peclet number of 20, okay, and the minimum node it require is minimum delta x, minimum number of cells it requires is going to be 10. Okay, so if Peclet number is 20, 20 divided by 10 is, your local Peclet number is going to be 2. If your local Peclet number is less than or equal to 2, you are going to get normal solution. Let's say you calculate this. So for a Peclet number of 20, and for nodes 11, which means you have 10 delta x, right? 10 cells. Okay, for a central differencing scheme you are getting a physical solution. Similarly, for upwind scheme also you will get a physical solution, but central differencing would be more accurate. If you see, the error is 0.014. For upwind it would be less accurate, 0.03, right? So uh, so what this essentially tells is, if you have higher order schemes, you are going to end up in getting dispersion errors, right? So to avoid those, your local Peclet number should be less than or equal to 2. So let's say if you have 50, okay, 50 is the Peclet number. What is the minimum number of nodes I need to have a physical solution? So remember, Peclet number should be less than or equal to 2. So
More than 50, I guess.
if it is more than 50, let's say 51, okay, which means 50 delta x, you are going to get good solution. But is this minimum? So can you calculate Peclet number for this local Peclet number, which would be 1, right? Local Peclet number would be 1 because 50 by 50.
Yeah,
So
that's true.
right. So what you can do is you can write 25. If it is 25, what happens? Local Peclet number is equal to 2. Still you can get like solution, a good solution, I mean the physical solution. So if it is less than 25, what you are going to see is you are going to see a unphysical solution. So what this really tells is, if you want to have a stable solution in a steady state, you should have a local Peclet number to be less than or equal to 2. Okay, so if it is an upwind, you no need to worry. But the problem with upwind is, you see there is a lot of errors, right? So for a Peclet number 50, your solution is here, the red one, but your blue one is the numerical solution, and you can simply see that it is more diffusive, right? So if Peclet number is 50, convection flux is more, 50 times more than the diffusion flux. But the numerical solution gave is, so if you plot for 18, Peclet number 18, let's say, this exact solution and Peclet number 50's numerical solution would be same, which means that for a Peclet number 50, the new upwind scheme is giving solution for Peclet number 80, which essentially tells that it is more diffusive. So that's why the odd, uh, you know, order of discrete odd like upwind is a first order, right? It is an odd order of uh, the, what do I say? The truncation term is in the order of odd numbers. So if you have that, you are going to have a diffusive scheme, right? If it is going to be even order, you are going to have a dispersive scheme. So that's what you might have learned in lecture also. So here I am just showing you the results, but I encourage you to get these results by yourself, by uh, you know, programming yourself in MATLAB. So do let me know if you face any difficulties. Um, uh, Update me if you get a solution in the next class. Okay. So from by here I will stop. You can leave. If you have any questions, you can stay back and ask. Thank you very much. Sorry for taking more time again.
Hello.
Yes, Nidhar.
ஹலோ பிரதர், கொஞ்சம் தமிழில் பேசலாமா? பிரதர், ஆக்சுவலி எனக்கு கொஞ்சம் ஒரு பேசிக் டவுட்ஸ் இருக்கு எனக்கு இதில். ஆக்சுவலி நம்ம இந்த கோர்ஸில் ஆரம்பிச்சதுலேருந்து கொஞ்சம் இந்த டிஸ்கிரிட்டைசேஷன் ஒன்று பண்ணுறோம் பார்த்தீங்களா?
ஆமாம்.
அது ஆக்சுவலாக இந்த டிஸ்கிரிட்டைசேஷனா என்ன, அது எதுக்காக பண்ணுறோம் இந்த இந்த கோர்ஸில்?
Right. So okay. So I will show you. So why do we need to do discretization is
Yeah, and what is first discretization and why we need that?
okay. So I will simply explain to you. Okay. So let's say you have a differential equation. Let's say that I think that was our agenda of first class. Anyway, so let's say you have you know this equation, right? Let's take a continuity equation. Okay, by dou x plus dou v by dou y plus dou w by dou z is equal to 0, right? So u is the function of x, y, and z, right? V is a function of x, y, and z, right? W is a function of x, y, and z. Now you see uh, our uh, our variables of interest is these velocities, right? If you want to solve any flow problem, your variable of interest is these velocities, and you see you need to get a function like your solution should depend on x, y, and z. So, and you see this is a partial differential equation, right? So you have one PDE, but you need how many? Three, but you have three unknowns, right? So that's when Navier-Stokes equation comes, right? So, uh, one second. So, let's say you want to solve some problem like this, okay? Flow between parallel plates, okay? When you want to solve something like this, you have to have three velocities, right? Two velocities in this case because it's a 2D problem, and you are going to have a pressure, okay? So, if you want to solve this, it has to satisfy basic equations like conservation equation. There's going to be mass conservation, there's going to be momentum conservation, okay? So, you have three equation and you have three unknowns. System is closed, right? Till now, is this clear? So you need to
Okay.
solve some equation to find a solution, right? To
Okay.
find a flow
Okay.
problem solution,
Yeah.
right? So now,
But
yeah, yeah. So I will come to your question. So now, let's say you want to solve these three equations. Can you solve these three equations together by analytically in means of whatever we did today? Now, like we had a ordinary differential equation, um, uh, like we assumed the solution, we substituted it, we got the auxiliary equation, we got the complementary function, we find the particular integral, all these things we did. Similarly, can you solve this PDE analytically for any problem? Is this possible by seeing the complexity? You see, we have a partial differential equation. U is not dependent on only one axis, it depends on all three axes. And we have non-linear terms here. We have second derivative terms, we have non-linear terms again in these three. So it's kind of, three non-linear coupled partial differential equations, right? You need to solve these three together to get any solution, U, V, and W. So it's actually not possible to solve this equation. So that's why what we do is, this is a differential equation, we have to solve the differential equation. What we do is, we will convert this differential equation to system of linear algebraic equation. Okay, that's the main focus of discretization. Okay, we have to solve this differential equation. How are we going to do is we are going to convert this into a system of linear algebraic equation. So how do we convert it? That's where discretization comes. Okay,
so we are making that dou phi by dou x in the right hand side and another term on left hand side like that. Huh?
no, so um, like how do I put it? So you have some differential equation, you are not able to solve it, right? So
Yes.
so basic idea first. Let's understand the basic idea. You you have a differential partial differential equation and you cannot solve it, but you need to get the solution velocity to understand the problem. Is that clear?
Yeah, clear.
So now this equations are complex, right?
Hmm.
So what we do is we need to find the solution, and we have some domain. Inside that we need to find the solution, right? Let's say this is some square or cuboid domain here. Here u velocity and pressure you need to find, right? So you may not be able to get a continuous function because these equations are complex. You cannot solve it. You cannot apply any mathematical concepts to solve it. But what you can do is you can use something called discretization. Okay, you can use something called discretization to convert this differential equation to a system of algebraic equation. Okay, that is the main idea. So
Okay.
until
So
now, is it clear?
yeah, clear.
So now there is some black box called discretization, which converts this into. So why we need to convert into linear system of linear equation is you can solve it. So there is
Yeah, yeah.
something which cannot be solved, which is a partial differential equation that cannot be solved. One thing which you can solve is system of linear equation. So we need to go through a black box called discretization to get this equation,
Okay.
right? So until
Right.
until now it's clear, right?
Yeah,
So
clear.
now how do we do this discretization? Now what discretization does is you have some domain, and what you will do is you will pick some few areas of interest. Okay, let's say you have a domain and you want uh, uh, let's consider again a square domain. Okay, and you consider few areas of interest. Okay, I no need everywhere, like I no need a continuous function for velocity and pressure inside this domain. I only need a few points where these are my areas of interest, these are my nodes of interest, or these are my cells of interest. Okay, if you based on different methods. Okay, these are the areas of interest which I need values. Okay, so if I get the solution for these areas of interest, that would be my solution, and I'm happy with that solution. Okay, so that's what we need. So what discretization does is you need only solution at these nodes. So you approximate your differential terms using series and write the equation in terms of only these nodes. Okay, remember your partial differential equation is for the whole domain. It is not for single nodes. I mean, it should satisfy for single nodes also, small control volumes also, but partial differential equation is defined for the whole domain. Now you are okay with solutions only at certain nodes, right? So what discretization says is I provide you schemes such that converts this partial differential equation into a system of equation which you can solve it in terms of areas of interest you need. Okay, so you are converting a PDE into a system of linear algebraic equation, but that linear algebraic equation depends only on these nodes, and these nodes are your areas of interest. Okay, so that's the main aim of discretization, and how you are using is using Taylor series approximation. You are essentially approximating each and every term of the equation.
Okay, so to convert those partial differential equation into algebraic form, we are using Taylor series, right?
So
Okay.
we are using Taylor series, true. So
So
you
in
can come up with different ways also to do that. There are few things like polynomial fitting also you can use. You no need to use Taylor series. You can do. There are few advanced topics like Chebyshev polynomial. All those things are there. Anyway, at the end of the time, you need values at your areas of interest. You are trying to convert this PDE to a system of linear ODE, which is in terms of these areas of interest, so that you can easily solve it and get your solution. That's the final aim.
okay, so here where does the finite difference formulation come into picture?
So you are interested in some, so the areas of interest, there's this thing called areas of interest, right? So that's when there are these three different methods you have. So one is finite difference method, you have finite volume method, you have finite element method you have. So if your your areas of interest is fixed, like at these points I need velocities, I need pressures to fully know the flow physics inside a uh, domain. Okay, now this can be modeled using finite difference method, which essentially divides it into small finite lines, or finite uh, nodes. Okay, so you solve for that node, that is finite difference method. In finite volume method you will solve for this control volume, where the areas of interest, the point you need is actually surrounded by a control volume as control cell. Okay, that cells, number of the cells will be stacked like that. So that would be finite volume method. In finite element method, these nodes would be each and every elements connected together, right? So you can use different ways to solve it. So discretization is where these three differs. Like you can do finite difference discretization, you can do finite volume discretization, you can do finite element discretization. So only that is a way we are discretizing it. Difference is nothing but a bunch of nodes. Finite volume is nothing but bunch of control volumes, and finite element is a bunch of elements. That's all. So whatever we did here, backward difference scheme, all these are finite difference scheme, which is fairly easy to do it. Finite volume, you need to implement. Finite volume is also easy if you learn it, but comparatively, finite difference is easy to use it. But the problem is it doesn't follow the conservativeness, which is very much needed for a fluid flow problem. We need to conserve mass, momentum, and energy. So that's why people usually do CFD, which would be finite volume CFD.
Okay, okay, brother. So here, so finite volume obeys the conservativeness. So why we need to take care of stability and transportiveness?
Right.
Conservation is important so that no energy loss is there. So system is obeying the partial differential equation. So we must deal with conservativeness. So we need to deal with stability and transportiveness.
Right. So what you essentially do is as a discretization, um, you convert a PDE actually into a system of linear algebraic equations. So while doing that, it's actually an approximation for a PDE, right? There is a PDE. You are approximating it to a system of algebraic equation. So it's actually an approximation, which means there is going to be error coming with it. Okay, there's going to be error sticking with that approximation. So why we need to take care of stability is stability is purely due to round off errors. So when you have a um, yeah, like it depends on the uh, like what is the precision of your system is. So in that way also you can say, but basically it has some error, and you don't want that error to grow with time. Okay, so the that is why we need to have a stability. Since we do an approximation to a PDE, you don't want that error to grow with time. That's why we are concerned about stability. And while you are approximating a PDE, you should understand the flow physics also. So if there is a PDE and it governs that flow goes from here to there, you should your scheme also should take that into account. Like your scheme also should have a physical sense that flow will be going from here to there, right? That's where there is this transportiveness. I think that's what you meant about transportiveness. Um, so that's where these things comes into picture. Only thing is you are doing approximation. How how educated approximation you are making is measured by this stability and boundedness, all those things.
Okay, fine. So actually, The in lecture I saw regarding the diagonally dominant matrix. So it mainly deals with the transport units. It shows the transport units of the problem like that the lecture was there. So what is the link between the transport units and the diagonally dominant matrix?
Right. I'm not sure about what is transportiveness you mean. Um, Maybe I will look into that.
Okay,
Uh,
okay, okay.
I'm not sure in what way they say transportiveness. So anyway, but diagonally dominant is essential. But I will just tell you what do you mean by diagonally dominant. So when you have a diagonally dominant matrix, your matrix is going to be non-singular. So what do you mean by non-singular? What do you mean by singular? Singular
The,
matrix means
the answer is zero.
right. So actually singular matrix means the rank of the matrix is going to be less than the number of rows. Okay. So what essentially it means is you can't invert it. So
Ah.
basically what we are doing is we are doing inversion right here, A inverse. So
Hmm.
if your matrix becomes singular, what happens? You can't do this A inverse, which like then there is no point of doing all this discretization, right?
Hmm, hmm,
So
hmm.
so you should make sure your scheme ends up with a matrix such that it is diagonally dominant. How do you do that? Your AI, you see the AI, this modulus of AI should be greater than these two. If you ensure these two to be less than this AI, essentially your diagonal is going to be AI, right? And off diagonal is going to be these two. If it is diagonally dominant means diagonal element is more than the summation of all other elements. Okay, I mean there is a modulus also is there. So if you see this, either is is greater than or equal to, then it is diagonally dominant and you are purely going to get a solution. So if you look at these two, UDS and CDS, if you add these two, what happens? 2 by delta x square plus A times delta x, right? So essentially these the addition and the AI is going to be same. Either it should be same or it should be greater than. Okay. So then you will ensure there is a diagonally dominant, and so that your matrix doesn't become singular. And if your matrix doesn't become singular, you are going to end up in getting a solution, a proper solution, a physical solution at least. Okay. If it is not,
Okay.
it's going to be a problem. There is the whole point of discretizing, approximating, everything vanishes if you couldn't invert it. So regarding transportiveness, I'm not sure what they mean by transportiveness. Maybe I will look into it and I will get back to you later.
Okay, okay. Thank you, brother. So this phi equal to A inverse B we are taking.
Uh-huh.
That phi stands for any physical parameter
Uh,
at each nodes, right?
right, right. So
It may be
usually,
whether
uh,
it may be whether P or pressure at each node we are calculating.
exactly, exactly.
Oh, okay.
So velocity or pressure it can be. So,
Hmm.
but for a fluid flow problem, there is a proper way to solve this system of equation. We just solved a single equation, right? We didn't solve a system of equation. In a fluid flow problem, we have a continuity, two momentums we have. This we have only one equation. We solved only one equation. So you just need to invert it. But if you have system of equation, there is a special way to treat which equation to solve first or which equation to do approximation first. All those things will come in your lectures, later lectures. That is will be like solution to the Navier-Stokes equation. So
Oh,
that thing you will learn. But essentially, this phi is our um variable of interest
okay.
and at the
At
areas
your
of
node.
interest. At the areas of interest.
Okay, okay.
If it is a control volume also, you do the same thing. What will happen is AI will be, these coefficients will be based on the control volume approach. You might have seen that. It will be A east, A west, right? So here instead of I plus 1 and I minus 1, you will write uh, phi east, phi present and phi west. Something
Hmm.
like that you will write, right? And the
Okay.
coefficients will vary like AW, AP and AE. So essentially it again forms the same matrix. and the phi you get is your variable of interest are the areas of interest you need. That areas of interest you get it from meshing or node generation.
Okay, okay, okay. Thank you very much, brother.